Hi guys, we are back. We are back again with your discrete mathematics lecture series with the traversal and Eulerian graph. So, what is the traversal and Eulerian graph and bridge? What is the problem of bridges of Konigsberg? Okay, so let's start. The 18th century East Prussian town of Konigsberg include two islands and seven bridges. So this is the problem. Okay, so the Konigsberg bridges of problem based on this thing. The 18th century East Prussian town of Konigsberg include two islands and seven bridges. So here you can see these are bridges 1, 2, 3, 4, 5, 6, 7. These are island A, B, and these are the bank C and D in 7036. So, how can you do this by graphical representation? So, suppose we have four node A, C, D, D, B. So just this is the reflexive A to C and C to A, and this is also reflexive A to D and D to A. This is direct A to B and B to D, also direct and also direct. So what you see here, Euler proved that the multigraph is not traversal and hence that a walk in Konigsberg is impossible. So what this problem say? What is the deep think of this problem? Okay, so question is this: beginning anywhere. You can start from anywhere. You can go through this and go through this. Ending anywhere. You can end anywhere. Can a person walk through town crossing all seven bridges but not crossing any bridges twice? Okay, so this is the condition. You cannot revisit twice any bridges. Okay, so the pupil of Konigsberg wrote to the celebrated Swiss mathematician L. Euler about this question. Euler proved in 1736 that such a walk is impossible. So that time one scientist and one person, you can say, Euler proved that in 1736 is this you can't walk in this island by this problem. I already tell you, we can't revisit any bridge in twice. Okay, so what the Euler do? He replaced the island and two sides of the river by point and bridges by curve. So he just make a graph. So here you can see this is the multigraph. A multigraph is said to be a traversal if it can be drawn without any breaks in the curve and without repeating any edges, as you know, edges. Okay, is that is if there is a path which include all vertices and use each as exactly one. So you can use each as exactly one. Such a path must be trail. I already tell you trail. So if you are not aware of the trail, then please see our previous lecture and will be called a traversal trail. Clearly, a traversal multigraph must be finite and connected. So after this principle is that Konigsberg walk is impossible. So what is the solution of it? Suppose multigraph is traversal and that a traversal trail does not begin or end at the vertices P. Suppose, okay, so P is an even vertices. For whenever the traversal trail enter P by edge, there must always be a edge not previously used by which is trail can leave P. Okay, are you understand? Are you getting my point? Thus, the as in the trail incident with P must appear pair. So P is even vertices. There, if a vertices Q is odd, here, see in this graph, see in this multigraph. Okay, observe that the multigraph corresponding to the Konigsberg bridge problem has four odd vertices. Four. So thus one cannot walk through Konigsberg so that each bridge is crossed exactly once. Euler exactly proved the converse of our statement. Okay. So what is the theorem of it? This Euler, a finite connected graph is Euclidean if and only if each vertex has even degree. And here you know what is the degree and what is the even, what is the Euclidean. A graph G is called Eulerian graph if there exists a closed traversal trail. Okay, so that this is called Eulerian graph. Corollary: any finite connected graph with two odd vertices is traversal. A traversal trail may be begin at either odd vertex and will end at the other odd vertex. Okay, so this is the your another topic, Hamiltonian graph. So this is the Hamiltonian and non-Eulerian graph. This is the Eulerian and non-Hamiltonian graph. Okay, why is this? Why is this? So just see first this. So first know the what is the Hamiltonian graph. A Hamiltonian circuit is a graph G named after 19th century Irish mathematician William Hamilton. The name of Hamiltonian is taken from the its scientist name who discovered this graph. Is so Hamiltonian graph is a closed path that visit every vertices in G exactly once. So you can see every vertices visit only once. Okay, so you can remember by this line, such a closed path must be a cycle. If Z does emit a Hamiltonian circuit, then Z is called Hamiltonian graph. So just observe this, what is the Eulerian? Eulerian circuit traverses every edge exactly once, but may repeat vertices. Okay, vertices may be repeat. While a Hamiltonian circuit visit each vertices exactly once. Here you can see each vertices exactly once, but many repeated edges. Okay. So this is the difference between Hamiltonian and non-Eulerian graph.